Here we're going to derive the distribution of the sample range, and we're going to let the xi, or the data, be distributed with some f, where f is continuous and I goes from 1 to n, so we're going to take a sample of size n. The cumulative distribution function is just that. It's the probability that x is less than xi. That's the CDF of f. And the order statistics, often it's x and then the number in parentheses, but we're just going to call it yi, be the ith order statistic to hopefully reduce confusion. Where y1 would then be the minimum of the xi and yn is going to be the maximum. And so the sample range would be yn minus y1. So here is the joint distribution of y1 and yn. And I assume that you have some knowledge about order statistics and how to find the distribution of order statistics. If not, I'll have another video on this in a few days that we can reference. Now note that y1 must be less than yn by definition. So we're going to set up a mapping here. We're going to go from R2 space, which is y1 and yn, and we have to map it to R2 space. So the variable of interest is R, our sample range, which is the largest minus the smallest. Then we create a sort of a dummy variable to find the joint distribution, and then we integrate out this at the end. So this would be the distribution. The distribution of RS, or the joint distribution, would be the joint, which would be f of y1, yn, with these values plugged in for y1 and yn, and then times of the Jacobian, absolute value of the Jacobian, which in this transformation is 1. So if we plug in, so here's our joint density. So then we're going to plug in S for y1, and we're going to plug in R plus S for yn. And that gets us this. And note that S goes from negative infinity to infinity, but R must be positive because y1 is always less than yn. So R is positive. So now that once we have the joint distribution, we need to integrate out S, which then gives us this. So we take our joint density and integrate out S. Okay, so let's go through a quick example to illustrate this. We're going to let our data be uniform 0, 1, and I goes from 1 to n, so we're going to take a sample of size n, and then f of x in this setting is 1, and the cumulative distribution function of x is just x. Now we set up our mapping. This is the variable of interest, R1. Jacobian is 1, so the absolute value is 1. Now, for me, the tricky part is finding the area that we integrate. Okay, and so I always like to draw a picture of it. So if we let this be y1 and this be yn, first of all, y1 must be less than yn. So we're on this half of the over here on this graph, and they go from 0 to 1. So, but to map it to this one, how do you draw the picture? I like to look at the boundaries. So here, if we look at this boundary with the tick of 1, y1 is 0, this whole distance. So that tells me S is going to be 0. So we're going to be on this axis somewhere. And then if we go from 0 to 1, when y1 is 0, that means R goes from 0 to 1. So this boundary maps to this boundary. And then if we look at this one, here y1 is equal to n, no matter where we are in this line. So that tells me R is going to be 0. So that we're going to be on this graph, or on this axis somewhere. But y1 goes from 0 to 1, so that says S goes from 0 to 1. So this boundary maps to this boundary, and then you can do the same for that boundary. So now when we integrate out S, we go from this boundary to 0. Well, this is S equal to 1 minus R. So when we integrate using that formula on the previous page, we're going to go from 0 to 1 minus r. And we plugged in s to our distribution up. So the f of x is 1, so that's 1. And the cumulative distribution function, we plugged in r plus s and then s. But notice that this s cancels with this s. And then what is left are all constants with regards to the s world. So they can be taken out front. So out front we have n minus 1, r raised to the n minus 2, and the integral of 1 times that. And the integral of 1 is just s, and then we plug in these values here from 0 to 1 minus r. The 0 part goes away, and that leaves this as the sample distribution for the range when our data is uniform from 0 to 1. And this is a beta function. So hope you enjoyed it. I'm going to have many more videos coming. Please subscribe so you're notified when they arrive. Thank you. Bye.